So hello everyone, welcome to the lecture series in analytical chemistry, and today we'll be covering the next one in methods of osmometry. So let's get started. So just an overview of the points that we'll be covering in today's lecture. We'll go through the meaning of osmolality, osmolarity, and osmotic pressure, and what those different things mean. Colligative properties, osmoregulation in normal physiology, methods to do with osmometry, the clinical applications of osmolality, and calculated osmolality equations, as well as the osmolar gap. So what is osmolality? So going back to basic principles, osmosis is the process by which solvent moves from an area of low solute concentration through a semi-permeable membrane to an area of high solute concentration. It essentially relies on the chemical potential of water, where solutes reduce this, so water will flow to an area of higher solute concentration. A semi-permeable membrane is essentially permeable to solvent, but not solute. So semi-permeable membranes, such as cell walls, will enable the transmission of water, but not solute. Thus, changing in solute concentration will affect water ships from compartments. And solvent essentially passes through the membrane because of the inequality of the chemical potentials on either side of this membrane. And since the chemical potential of a solvent molecule in solution is less than in pure solvent, then solvent will spontaneously enter the solution until the inequality is removed. And the osmolality of a solution is the total concentration of all osmotically active species present. Molecules such as sodium chloride, which can dissociate into two ionic particles, sodium and chloride ions, will have an osmolality of approximately twice that of an equimolar solution of a species like glucose, which does not dissociate into its constituent ions. Whenever a solution is separated from a solvent by a membrane that is permeable only to solvent molecules, there is passage of solvent across the membrane into the solution. And therefore, a pressure differential develops across that membrane, which is referred to as the osmotic pressure. So the osmotic pressure is the pressure of this that will depend on the gradient in solute concentrations as separated by this membrane. And it is determined by the number of particles per unit volume of fluid. The osmotic pressure is essentially the amount of pressure required to stop osmosis from occurring. And the osmotic pressure being exerted by particles in solution is determined by the number of particles per unit volume of fluid. And each particle in a solution exerts the same amount of pressure against the membrane, regardless of its mass. So what's the difference between osmolality versus osmolarity? They're both units of solute concentration that are often used in reference to biochemistry and body fluids. They are measurements of the solute concentration of a solution, and in practice, there's a negligible difference between the absolute values of the different measurements. For this reason, both tend to be used pretty interchangeably, even though they refer to different units of measurement. So osmolality expresses concentrations relative to the mass of solvent, whereas osmolarity expresses concentrations relative to the volume of solution. Osmolality is a thermodynamically more exact expression because solution concentrations expressed on a weight basis are temperature independent, whereas those based on volume vary with temperature. So although the term osmolarity is often used in the medical literature, osmolality is what the clinical laboratory means. So moving on to colligative properties. This refers to the properties of solutions that depend on the number of molecules in a given volume of solvent rather than the properties of the molecules themselves. There are four properties of solutions. There's osmotic pressure, vapor pressure, boiling point, and freezing point. And all four of these are known as the colligative properties, and they are all directly related to the total number of dissolved solutes per mass solvent. So when you have an increased When you have an increased osmolality, you'll have an increase in osmotic pressure and boiling point, but a decrease in vapor pressure and freezing point. So in addition to the osmotic pressure being raised, when a solute is dissolved in a solvent, the vapor pressure of the solution will be lowered below that of the pure solvent, and as a result of the change in vapor pressure, the boiling point of the solution is also raised above, and the freezing point of the solution is lowered below that of the pure solvent. An electrolyte in solution dissociates into two dissolved ions in the case of sodium chloride. Therefore, the colligative effects that we just discussed of such solutions are multiplied by the number of dissociated ions formed per molecule. However, because of incomplete electrolyte dissociation and also associations between solute and solvent molecules, many solutions do not behave as the ideal case, and a 1 molal solution may give an osmotic pressure lower than theoretically expected. So there is a concept known as the osmotic activity coefficient, which is a factor used to correct for deviation from the ideal behavior from the system. So glucose has an osmotic coefficient of 1, whereas the osmotic coefficient for sodium chloride is 0.93 at the concentrations found in the serum. The electrolytes sodium chloride and bicarbonate, these are present in relatively high concentrations and thereby make the greatest contributions to serum osmolality. Non-electrolytes such as glucose and urea, which are present normally at lower molar concentrations, they contribute less. And actually serum proteins contribute less than 0.5% of the total serum osmolality, because even the most abundant protein is present at millimolar concentrations. And plasma osmolality is tightly regulated between approximately 280 to 295, and the total osmolality of a solution will be the sum of the osmotic pressures or osmolalities of all solute species present. So as cell membranes in general are freely permeable to water, the osmolality of the extracellular fluid is approximately equal to that of the intracellular fluid. Therefore, plasma osmolality is a guide to intracellular osmolality. And as mentioned, the normal osmolality of extracellular fluid is 280 to 295. Alterations in water homeostasis can disturb cell size as well as function. Although most cells can regulate cell volume in response to osmolar stress, neurons are particularly at risk. So regulating water balance and having a stable water homeostasis is fundamental to survival. And this is important because changes in ECF osmolality can have a great effect on ICF osmolality, and these changes cause problems with normal cell functioning and volume, and they can even cause cytolysis. And as you can see from the diagrams below, can result in either extreme, whether it's cell dehydration or cellular edema. So that brings us on to osmoregulation, where the kidneys play a fundamental role in maintaining the osmolarity of body fluids. Plasma osmolality is tightly regulated to prevent that cell swelling or shrinkage. And it's regulated essentially by controlling water influx and efflux from the body. So only the intake of water through drinking and output via urine loss are controlled physiologically. And this is the important way that we regulate plasma osmolality. It's by generating urine of different concentrations. And if the body must conserve water to replace excess loss, then urine is more concentration. And vice versa, if the body needs to lose excessive water, then urine is less concentrated. So in normal physiology, increased osmolality in the blood will stimulate the secretion of antidiuretic hormone, ADH or ABP. With mild dehydration, plasma osmolality rises slightly, and this increase is detected by osmoreceptors in the hypothalamus, which stimulates the release of ADH from the posterior pituitary. This will result in increased water reabsorption, more concentrated urine, and less concentrated blood plasma. If plasma osmolality decreases slightly, the opposite occurs. So a low serum osmolality will suppress the release of ADH, so you've got a negative feedback loop, resulting in decreased water reabsorption and more concentrated plasma. And as mentioned, this whole system is regulated by the hormone ADH. So an increase of only 2 to 3% in plasma osmolality will produce a strong desire to drink, whereas a change of about 10 to 15% in blood volume or arterial pressure would be required to produce the same response. So our bodies are very sensitive to small changes in plasma osmolality. So focusing a little bit more on the kidney, we know that water always follows an osmotic gradient, and most cell membranes are freely permeable to water. But the main exceptions to this are the membranes of the cells lining the collecting tubules in the kidney, which only become permeable to water in the presence of ADH. The cell membranes are selectively permeable to solutes such as sodium and glucose, which is modulated by hormonal action. So regulation of urine volume and osmolality are major functions of the collecting ducts. By varying the amount of water that is recovered, the collecting ducts play a major role in maintaining that body's normal osmolality. If the blood becomes hyperosmotic, the collecting ducts recover more water to dilute the blood, and vice versa. The collecting ducts will recover less of the water if the blood is hypoosmotic, leading to the concentration of blood. When stimulated by ADH, aquaporin channels are inserted into the apical membrane of principal cells, which line the collecting ducts. As the ducts descend through the medulla, the osmolality surrounding them increases. If aquaporin water channels are present, water will be osmotically pulled from the collecting duct into the surrounding interstitial space and into the peritubular capillaries. Therefore, the final urine will be more concentrated. If less ADH is secreted, fewer aquaporin channels are inserted and less water is recovered, resulting in more dilute urine. So in essence, by altering the number of aquaporin channels, the volume of water recovered or lost is altered, and this in turn regulates the blood osmolality, blood pressure, as well as the osmolality of the urine. So moving on to osmometry. What is it? It's a technique for measuring the concentration of solutes that contribute to the osmotic pressure of a solution. And most modern osmometers share a common principle in that they measure the osmolality of a liquid sample by comparing a particular parameter of the solution, such as its freezing point, to the same parameter of the pure solvent, for example, water. And essentially, we're using an osmometer to measure collective properties, vapor pressure, freezing point, and also a membrane osmometers, which look at colloid pressure. These are the three major types of osmometers commercially available, and they each leverage a particular colligative property to achieve their analytical results. With freezing point osmometers, they determine the osmotic strength of a solution by utilizing freezing point depression. By using vapor pressure osmometers, they determine the concentration of osmotically active particles that reduce the vapor pressure of the solution. Membrane osmometers, they measure the osmotic pressure of a solution separated by a semi-permeable membrane. So they all have different underlying principles, but they use the colligative properties that we discussed earlier to do with the osmolality of a sample. So starting off with freezing point depression. So these osmometers monitor how a sample's freezing point changes according to its solute concentration. Its measurement principle is based on the colligative property of freezing point depression. So if a solute is added to a liquid, this results in a decreased freezing point of the solution. When a solute, the particles, are dissolved in a solvent, the freezing point of that solution is lower than that of the solvent alone. So as more solute is added, the freezing point decreases further. So by precisely measuring the freezing point of the solution, the osmolality or the concentration can be determined. Freezing point measurement is non-specific, so it won't tell you what the particle is, nor will it tell you the size or the shape of the particle. It only depends on the number of particles in that solution and not on the physical or chemical properties of the solutes. So due to this linear correlation, the osmolality of a sample can be determined by precisely measuring its freezing point. And the components of the freezing point depression osmometer includes a thermostatically controlled cooling bath, or a block that's maintained at about -7 degrees, a stirring wire, which is a rapid stir mechanism to initiate the freezing of the sample, a thermistor probe connected to a circuit to measure the temperature of the sample. A thermistor is a glass bead attached to a metal stem whose resistance varies rapidly and predictably with temperature. A galvanometer that displays the current from that thermistor and then is used as a guide when the measuring potentiometer is used. So the best way to show the principle of this is to share a video, which I will play.
Let's take a closer look at what happens inside the osmometer when a freezing point measurement is made. Once a sample is introduced in the cooling chamber, it is rapidly supercooled to a predetermined temperature below the expected sample freezing point. This rate of cooling is tightly controlled by the osmometer. While the sample is in the supercooled state, a physical shock called the freeze pulse is introduced to the sample. As a result, the sample becomes partially crystallized, forming an ice-water mixture surrounding the temperature probe. The heat of fusion resulting from the crystallization process raises the sample temperature to a plateau where the liquid-solid equilibrium is maintained. This temperature plateau represents the true freezing point of the solution. The osmometer precisely measures this temperature at the plateau and calculates the concentration in milliosmoles per kilogram of water. This is the test result reported by the osmometer.
Okay. So essentially, the plateau in temperature is the freezing point when the latent heat of fusion and the abstraction of heat from the cooling bath are in equilibrium, and the measurement is taken at this point. And freezing point is inversely proportional to osmolality. So what are the pros of freezing point depression? They deliver the most rapid and accurate results with only very small sample sizes required. They're ideal for dilute biological and aqueous solutions. They're simple, they're reliable. It's the industry preferred method. But samples must be of low viscosity, and it may not be suitable for high molality colloidal solutions. Moving on to the next method, known as vapor pressure. So this is the pressure exerted by a vapor in thermodynamic equilibrium with its condensed phases, i.e. solid or liquid, in a closed system. So a liquid will evaporate at all pressures below its vapor pressure and remain stable at all pressures above the vapor pressure. And vapor pressure osmometers, they determine the concentration of osmotically active particles that reduce the vapor pressure of that solution. So they use this relationship between boiling point and vapor pressure to measure solute concentration. And boiling point is when the atmospheric pressure equates to the vapor pressure. As the temperature rises, the vapor pressure overcomes atmospheric pressure and the vapor ensues. So a substance with a high vapor pressure at normal temperature is considered to be volatile. Vapor pressure osmometry, it provides a flexible and robust method for determining osmolality. And again, it results in highly accurate and reproducible osmolality measurements. And in addition to quantifying osmolality in liquids, it's also commonly used to determine the number of average molecular weights of polymers in solutions of known mass concentration. So it has a few different uses. The way it works is that a thermocouple sits inside a small sealed chamber. So the first step requires loading the sample solution onto a solute-free filter paper and inserting that into the chamber. And the sample inoculated paper is then loaded into the sealed measurement chamber, as you can see in step 2. The third step is where the temperature of the chamber and the solvent vapor inside are allowed to equilibrate, typically just for only a few seconds, and that's known as thermal and vapor equilibrium. And then in the fourth step, the thermoelectric cooling cools the thermocouple to below the dew point of the vapor, Cooling is then stopped and the condensation begins to form and warms the thermocouple. And the solvent vapor then condenses onto the thermocouple in step 5. The latent heat of vaporization heats that thermocouple and the temperature rises towards the dew point temperature. So measurement is related to this concept called dew point rather than the vapor pressure itself. And dew point is the temperature at which the condensate is equal to vapor, and dew point decreases with decreased vapor pressure. So in the final step of measurement, the thermocouple temperature stabilizes as vapor condensation slows, determining that dew point temperature before eventually rising again towards ambient temperature. The solution osmolality is then calculated internally by a calibrated instrument from the dew point temperature depression. So as you can see in the graph, that dew point temperature depression is what allows the calculation of solution osmolality via this method. So what are the benefits? So they, again, perform rapid and inexpensive measurements. You can use small sample size, but really vapor pressure osmometers are unable to test high molality or colloidal solutions. And there's a major drawback in that they also cannot detect volatile solutions such as alcohol, which in clinical practice is quite an important use of osmolality when you have a physician suspecting that a patient has ingested something like methanol or ethylene glycol. So this is a major drawback in this particular method, in that it deprives the physician of important information needed to treat the patients in suspected cases of overdose or ingestion of toxic substances. So that is the major drawback with this method. It's also less accurate than freezing point osmometry. So as a result, freezing point depression is preferred in clinical practice. And then finally, colloid osmotic pressure. And this is also known as membrane osmometry. And it's a technique for the determination of molecular masses of polymers by means of osmosis. And the detection of the osmotic pressure can be determined into the number average molecular weight of that polymer. And the measuring cell consists of about 2 chambers separated by a semi-permeable membrane. And the sample is placed on one side of the membrane, and the colloid-free physiological saline solution is placed on the other reference side, where the reference cell is. And the measurement principle is based on a measuring cell consisting of an upper and a lower half, which is separated by this membrane. And the so-called reference cell is equipped with a pressure transducer. And both cells contain a solvent. And then after adding a sample with a higher colloid osmotic pressure, for example, the serum or the plasma, to the sample cell, permeation of the solvent causes pressure in the reference cell based on osmosis, i.e. the solvent will move via osmosis from the saline side. And then this is measured by a pressure transducer, which is amplified electronically and then displayed as positive direct colloid osmotic pressure. And these pressure sensors tend to be very sensitive and they can detect that difference in pressure. So the change in the compartment volumes are essentially directly related to the osmolality in the sample. But so there are benefits with this method in that it provides potentially unlimited direct measurement of osmotic pressure and solution osmolality. And there's no limitation on the sample concentration, and it can also determine the molecular weight of macromolecules. But it is hard to synthesize a membrane that is selective enough. It's also very time consuming, difficult to operate, and in contrast to the other methods, requires a larger sample volume. And the results can be quite irreproducible. So in essence, it's only good for looking at larger molecules such as proteins, and it's not in routine use amongst clinical labs. So it goes without saying which of these are most widely used by almost all the UK labs. And that's because freezing point depression, it combines all of the advantages whilst showing none of the disadvantages of the other forms of osmometry, such as a longer testing time or the inability to test high molality or colloidal solutions. So the test times take about maybe 2 minutes, and the repeatability is quite impressive. It's in the range of plus or minus 2 milliosmoles per kilogram. You only need a small sample size, and the typical sample volume is in the microliter range, which is pretty advantageous for when you have limited samples in the clinical lab settings. It's also quite simple to use in that it requires little knowledge or scientific background to operate it and still achieve good reproducible results. And they work pretty well with most liquid matrices. So in clinical practice, we look at urine and plasma osmolality, and it's the most widely referenced and practiced technique for osmolality testing. So virtually all clinical laboratories will use this method because of its simplicity. And importantly, as we mentioned, the fact that vapor pressure osmometers will not detect volatile substances like methanol, ethanol, or isopropanol. And in addition, freezing point depression, unlike vapor pressure, is independent of changes in ambient temperature. So just a few clinical applications. So we can use this method to look at both plasma and urine osmolality, and the determination of these can be really useful in the assessment of electrolyte and acid-base disorders. And comparison of the two can determine the status of water regulation by the kidneys in settings of severe electrolyte disturbances, where patients are presenting with polyuria, as might occur in diabetes insipidus or in syndrome of inappropriate antidiuretic hormone. And the comparison of calculated versus measured osmolality can also reveal the presence of something called an osmolar gap, which can be important in determining the presence of an exogenous osmotic substance. This is an important clinical application in cases where there is suspected ingestion of toxic substances such as ethylene glycol or methanol. Comparison of calculated and measured osmolalities can also confirm or rule out suspected pseudohyponatremia as caused by the electrolyte exclusion effect. So how do we calculate osmolality? As mentioned, there are major osmotic substances. The major osmotic substances in plasma are sodium, chloride, glucose, and urea. Thus, the expected plasma osmolality can be calculated from this equation that incorporates those osmolytes. The 9 that is added represents the contribution of other osmotically active substances such as potassium, calcium, and proteins. And the 1.86 is 2 times the osmotic coefficient of sodium, which we mentioned earlier, being 0.93, because it reflects the contributions of both the constituent ions, i.e. sodium and chloride. But note there are various versions of this equation. Some don't include the 9 milliosmol per kilogram factor, and others do include potassium, and others round up the 1.86 to 2. Osmolar gap is the measured minus the calculated osmolality, and a high gap over 10 indicates the presence of unmeasured osmotically active substances. So this is very useful in clinical practice where there is concern of ingestion of toxic substances, often alcohols. And then just a quick note on pseudohyponatremia. So each liter of plasma contains about 930 mils of water and 70 mils of proteins and lipids. So in cases where there are high lipids or proteins, this reduces the plasma water and therefore plasma sodium, measured per liter of plasma, which is artifactually low. But in cases like this, plasma osmolality should be unaffected because the osmometer measures only the sodium activity in the plasma water. So plasma osmolality should essentially be normal in cases where you have high proteins or lipids causing an artifactual pseudohyponatremia. Where hyponatremia is associated with an increased serum osmolality, known as hypertonic hyponatremia, so you have high plasma osmolality with a hyponatremia, then this would suggest the presence of excess effective osmoles other than sodium in the extracellular fluid. And this type of hyponatremia is most frequently encountered in patients with hyperglycemia. The elevated glucose concentration provides effective plasma osmoles, resulting in diffusion of water from the cells, ICF, into the ECF, therefore decreasing the ICF, expanding the ECF, and decreasing the serum sodium concentration. This relationship can be quantified. So they say for every 5.6 millimole per liter increase in the serum glucose concentration, you get a serum sodium concentration decrease of about 1.7, and the serum osmolality increases as well. But this correction is only a rough estimate because the decrease in the serum sodium concentration may vary significantly with any degree of hyperglycemia. Other substances like mannitol that do not cross cell membranes also provide effective osmoles and can also cause hypertonic hyponatremia. And the presence of any of one of these unmeasured osmoles should be suspected in patients with hypertonic hyponatremia if there is a significant osmolar gap. So given the prevalence of disorders of hyponatremia in practice, the measurement of plasma osmolality, whether it is associated with a normal osmolality or whether that hyponatremia is associated with a high osmolality and therefore known as hypertonic hyponatremia, it serves as an important role in the assessment of this electrolyte disturbance within the clinical setting. So some take-home messages. Dissolved solutes will result in a solution with increased osmotic pressure and boiling point, and a decreased vapor pressure and freezing point. These terms are known as colligative properties, which underpin the principles behind osmometer measurements and the various type of methods used. Freezing point depression is the most commonly used technique to measure osmolality in clinical laboratories across the UK. Comparison of plasma versus urine osmolality is clinically useful in the assessment of water balance disorders. An osmolar gap between the measured and calculated osmolality can reveal the presence of unmeasured osmolytes, which serves a very useful tool in clinical practice where there is clinical suspicion of the ingestion of toxic substances. Thank you for listening.